For our MECH2409 design project, Alexia, Neha, and I have decided to construct a prosthetic leg. For this project, our team focused on a transtibial prosthesis, also known as a below-knee amputation, which is an artificial limb replacing the tibia and fibula cavity, which resides below the knee. This also includes the ankle and foot being replaced as well. So on to our final design. The main body of our prosthetic is composed of a titanium aluminum alloy, which is listed on the screen, and a spring that will be made of a chromium or carbon fiber material located on the foot of the leg that resides below the ankle. The amputated leg sits in the knee socket, and the spring aids in organic leg movement for compression. The bar attaching the knee socket to the leg allows for rotation and bending for the knee. When performing the finite element analysis, we tested each individual part separately. So that would consist of the cup that holds the knee, the tibia and fibula cavity, and the ankle and foot pieces. This testing was done to be able to hold a force of 511 newtons, as that corresponds to the weight of our model subject with a height of 4 feet 11 inches.
Two common loading conditions that individuals experience are compressive loads from the weight of a person and bending loads, often from physical activity. The first load, compressive load, was the most common loading condition that a prosthetic leg must be able to withstand. This would be classified as a static load due to it being a constant force over a long period of time. Therefore, the prosthetic leg would have to be able to support this compressive load at minimum. After performing the stress analysis, the results showed the absolute minimum stress of 2.757 times 10 to the negative 2 newtons per meter square, and maximum stress being 1.378 times 10 to the 7 newtons per meter square across all parts. By this information, our prosthetic leg is capable of withstanding a considerable amount of stress. The results showed a very small value of displacement, with the absolute minimum being 0 millimeters and the maximum being 4.13 times 10 to the negative 5 millimeters, which implies that there will not be a significant amount of deformation. The values obtained for strain had a minimum of 3.562 times 10 to the negative 13 and a maximum of 5.245 times 10 to the negative 5. The safety factor obtained for each part of the prosthetic had an absolute minimum of 6.002, which implies that any conditions below that value would cause our prosthetic to break.
We based our type of fatigue loading conditions off of an athlete's rigorous movements. This is considered a cyclic loading force because it's repeated over the course of their athletic career. The motion at which an athlete applies a perpendicular force to their prosthetic foot, it would cause a bending between the ankle and knee due to the bottom of the foot being fixed. By this, we mean our boundary loading conditions stop at the foot as a grounding mechanism. We simplified this scenario to mimic a cantilever beam. When performing the fatigue loading conditions, we overestimate our cycles to about 1 million to gather an over-exaggerated result. It was found that with the Gamage plot, the value stayed constant with a value of 100. When looking at the life plot, it shows that the prosthetic is estimated to have a lifetime of 1 times 10 to the 6 cycles, which fits our given input. Essentially, based off of our two results regarding our fatigue analysis, we gathered that it would not fail over the given cycles provided.